today I'll be talking a little bit about combination of several technologies. Some of these combinations actually originated in my lab, and I should make a disclosure because in the photosensitizer side, we have some photosensitizers that were licensed to a startup company that is now a pharmaceutical company. And in some of the technologies, we also have patents, and these have been licensed to another company called LaserLeap. So Lucidin and LaserLeap are companies that emerged from some of the work that I'm going to present here. We have had this very nice introduction of what happens with light when it penetrates tissues, just given by Paula. And from the phenomena associated with the diffusion of light in human tissues, you can get information from the scattering and from the absorption, from intrinsic chromophores of the skin of the human tissues. I will, for this audience, skip most of this information because you are all familiar with them, what contributes to the scattering and what contributes to the absorption. In fact, the absorption comes basically from the electronic absorption, from dyes, endogenous dyes, and also from the vibrational overtones that are excited, mostly of water in the near infrared. But both of them contribute to the absorption and to the scattering of light in tissues. It is convenient to characterize this in terms of an optical penetration depth, as it is defined here, which will depend on the absorption and scattering coefficients. And I think the number to remember out of these equations essentially is that for 3 times the optical penetration depth, you have lost 95% of the light. And this depends on the wavelength. As you see here for skin, the optical penetration of light in skin depends strongly on the wavelength increases up to the near infrared. Then there's a dip here that is related to absorption by water. You have some more windows over there, but in general, this is the region where people prefer to work at 400 nanometers. What you can, the information you can get is very, very superficial, not really very interesting. And after 630 nanometers, then it becomes more interesting. As I mentioned before, this comes from both scattering and absorption. The molecules responsible for absorption in human tissues are identified here. And you see that there is a window in this slide called phototherapeutical window, because this was meant more for the phototherapy approach, but also corresponds basically to the photodiagnostics window. In photodiagnostics, you can go to longer wavelengths. In phototherapeutics, you cannot, because then the energy available in each photon is much less and insufficient to produce desired therapeutic results. But most of the work then has been focusing in the use of wavelengths between 630 and 900 nanometers. For photodiagnosis, of course, we take advantage of absorption and scattering. This was precisely the topic of the previous speaker, so I will not be addressing that in this talk. I'll be talking essentially about the fluorescence and the radiationless transitions. Of course, the fluorescence is quite obvious that you can detect the fluorescent. The fluorescence comes from both endogenous dyes present in the organs, present in the tissues. We can add, and this was actually one of the questions asked to the previous speaker, we can add exogenous dyes, contrast agents, to improve the fluorescence, and we'll see some examples of that. But also from the radiationless transitions, you can also obtain information for photodiagnosis. In fact, when you're using pulsed lasers, this release of thermal energy is very rapid and gives rise to photoacoustic waves. So photoacoustic waves are generated by pulsed light of human tissues. In the endogenous dyes, it's mostly hemoglobin, oxy and desoxyhemoglobin that give rise to signals. and they can be detected. And photoacoustic tomography is based basically on the radiation-less transitions resulting from pulsed light absorption by endogenous dyes. In some circumstances, we will be also interested in phototherapy, and hence the topic, theragnostics, because if you generate the triplet state of an endogenous sensitizer, or preferably of a dye that you add, and in these cases, we call the dye a photosensitizer. So if you have a photosensitizer that goes to the triplet state, then it can transfer energy to molecular oxygen. And from this energy transfer process, several things result. The most important of them is the generation of singlet oxygen. Singlet oxygen is a reactive oxygen species and can attack some of the biomolecules present, oxidize them, and this can trigger cell death. So you can kill cells by using photosensitizers, light, and oxygen at the same time. This is called photodynamic therapy. Now, the endogenous dyes can be a problem in many instances if you're looking into fluorescence, and we'll start looking with fluorescence. As I mentioned before, Paula talked about absorption and scattering. I'll be talking about fluorescence and radiation-less transitions. So in fluorescence, you have this endogenous fluorescence. This is a very simple experiment that you can run with many commercially available equipments these days, where you excite at a given wavelength, in this case 500, you detect fluorescence at another wavelength. And if you are exciting at lower wavelengths, you have this endogenous fluorescence. If you have the two wavelengths very close together, you are blinding yourself with excitation. That's why the intensity in this case is so much higher. So you need to separate excitation and detection of fluorescence. If you move to longer wavelengths, then the endogenous signal is substantially reduced. In fact, in this case, what we are seeing here at 745 is a very small signal that came mostly from the stomach of the mice, and it's probably related with diet and not really an endogenous diet. The diet of the mice includes chlorophylls and things like that, and this is probably what is emitting from the stomach. So in this region, in fact, there's a very black background that will favor, let's say, detection of fluorescence coming from a dye that is administered to the animal. In this case, it was ingested, but it's basically the same principle. And this basically recalls a little bit what I've been saying before. We can detect above 800 without much contamination, but if you excite at low wavelengths, then you still have this kind of contamination. In this case, again, this is mostly the diet of the animals, but also some signal coming from elsewhere. So ideally, we would like to excite at long wavelengths, detect at long wavelengths, to get rid of the signals from the endogenous dyes. And many efforts have been done in the literature to find fluorophores that meet these criteria. There is a very nice paper published by Brian Polk last year, where he gathers lots of information concerning such dyes. In fact, the dyes that are used today as fluorophores start being used as absorbers. So when they were first approved, and this refers to FDA approvals in the United States, when they were first approved, they were approved for applications where what mattered was the absorption of light. But later on, with development of other technologies, it became clear that it would be better used as fluorescent dyes. So you have here a number of fluorescent dyes. It's not a very large number. You have indocyanine green and fluorescein, which by large represent most of the market today, both in fluorescence procedures and in absorption. Some of the procedures are identified here. And more recently, you have another product that came. I'll be discussing this a little bit more in detail. Aminolevulinic acid, which works by a different principle, and I think it offers many interesting opportunities for further development. The dyes that I mentioned before follow approximately the principles that we have discussed before, that is absorption in the near infrared, and the fluorescence then becomes quite clear. For fluorescein, the absorption and emission are still around 500, and fluorescein can only be used for very superficial detections. It is okay to use it, and this is the reason why it was approved for diagnosis in the eye, for example. But there is a strong limitation on the depth of the analysis that one can perform with fluorescein. The work here is in fact something that we have done trying to improve such dyes. It's just an example from some optimization of the properties of fluorescent dyes that we did in our lab to illustrate that we can further progress in this field, find better dyes that we can use for as fluorescence markers. This was a series that we have studied. The things to take into consideration is the wavelength where they absorb, in this case, all of them above 700 nanometers. The Stokes shifts, because we don't want to have contamination between the excitation and the detection of the emission. Of course, we want to have high fluorescence quantum yields. This is the generation of singlet oxygen. If we generate singlet oxygen, it's likely that you'll have some toxicity, and some of them do generate singlet oxygen. And then we don't want them to bleach very quickly, and this is the photo decomposition quantum yield. If they bleach quickly, we will have the signal disappearing as we are making the collection of the fluorescence, and this is definitely not good. Our work led us to the selection of this specific molecule to make some trials with animals. And what you see here is the fluorescence of this dye administered by intravenous injection to mice, and the fluorescence after 1 hour, 4 hours, and 24 hours. You see that the fluorescence goes up and then goes down because there's elimination of the dye. Probably in the liver, this is the region of the liver. When these animals are inoculated with a tumor, and we are going to see here the positioning of a tumor in the mammary gland. It's an orthotopic 41 tumor. It is a biopsy mice tumor that mimics relatively well the triple negative breast tumor in humans that Paula mentioned before, which is in fact a very problematic tumor because it doesn't respond to most of the therapies and is responsible for most of the cancer deaths in women. What we do here then is to have an initial signal before we make the administration of the dye. As you see, because we're exciting at long wavelengths and detecting in even longer wavelengths, autofluorescence is very small. After the administration, the dye is a little bit distributed, but you do see that some of the dye does tend to accumulate in the mammary gland, as we see here. And finally, after a few days, it's totally eliminated. These specific tumor cells were modified to express luciferase so that we could at the same time do bioluminescence. Of course, bioluminescence is much better to detect anything. You can see maybe 10 cells if they are bioluminescence, but these tumors don't occur in nature. So it's good for the comparison, but it's not of clinical relevance. The tumors that would be of clinical relevance is this one. And what you see here is that we have a contrast ratio of 2.5 for a 1 millimeter tumor, which is non-palpable tumor. We cannot see that the tumor is there, but with this technology, we see some fluorescence, increased fluorescence coming from the tumor. An alternative, perhaps more interesting than the one that we have been developing, is to target the cells specifically. And this case that I'm showing here is a recent example that was approved by the FDA for a dye that is used to visualize malignant tissue during surgery. what is done here is to administer not a dye, but a precursor. This is the precursor, aminolevulinic acid. It goes through a series of steps in the biosynthesis of an endogenous dye, which is protoporphyrin IX. Protoporphyrin IX is fluorescent. This is what is actually seen in the open field by the surgeon during the procedure. There is an accumulation of protoporphyrin in cancer cells because they have an increased metabolism, and also because the feedback mechanism that controls the synthesis of protoporphyrin IX is not working when we are administering an exogenous dye. So in a few hours, typically 3 to 4 hours after the administration of 5-ALA, you start having an increased fluorescence from tumor cells. So this is based on the metabolism of tumor cells. I think there are great opportunities to take advantage of other specificities of tumor cells, like, for example, having a fluorescent dye attached to an antibody or to a molecule that has a specific receptor at the surface of the tumor cell. And there are many, many opportunities, I believe, for further development here. This photosensitizer, protoporphyrin IX, is in fact very well known in photodynamic therapy. It's one of the commercial successes of photodynamic therapy, because much before ALA was used in visualization of malignant tissue, it was already used in the photodynamic therapy of skin lesions, in particular of actinic keratosis, and also in some cancers like basocellular cancer. The reason why it was used in dermatology is because the molecule that is administered is of small size, can permeate the skin relatively rapidly, and then it accumulates in the tumor tissues by the reasons that you see here. And when it accumulates, you have protoporphyrin there, and you can do photodynamic therapy. Briefly, in photodynamic therapy, you have, well, this one is illustrating photodynamic therapy by intravenous injection, but the case I was talking about is a case of topical application of a photosensitizer. But the principle is the same. Once you do the topical application, you have the photosensitizer in the tumor region, you excite with light, and in the presence of oxygen, you have energy transfer from the photosensitizer, could be protoporphyrin IX, to molecular oxygen, gives rise to the singlet oxygen and other reactive oxygen species that will kill the tumor cells, specifically in the place where the elimination was made. Protoporphyrin IX, as I said, is a well-known photosensitizer. It has been in clinical practice in photodynamic therapy for more than 30 years. The structure is here. It is relatively efficient in generating singlet oxygen. The quantum yield is 0.77. So in fact, it's a very good photosensitizer in this respect. It does have the problem that its absorption in the red is very small. The absorption coefficient is about 5,000, and additionally, it is not a very stable molecule. This is why, rather than using protoporphyrin IX, people doing photodynamic therapy use 5-ALA, which is a precursor, and then protoporphyrin IX is biosynthesized and used as in situ. What has been used quite often in photodynamic therapy is photofrin. Photofrin is a derivative of hematoporphyrin. It was approved for various types of cancers about 30 years ago. There are two problems with photofrin that limited its application in photodynamic therapy. One of them is, again, the small absorption in the near infrared, where we want to excite. And second one, it is that it has a very long elimination lifetime. So the patients, once the administration of photofrin is made, have photofrin in their body, especially in their skin, for a long period of time. So they have to stay in the dark for at least 2 to 3 months, which is definitely not something that is acceptable when you're treating patients with advanced cancer and their life expectancy is relatively short. Our contribution here was development of a photosensitizer called radaporfin, which has a much higher absorption in the near infrared and has a shorter illumination lifetime so that we can administer it. It's more efficient absorbing light, it's more efficient generating reactive oxygen species, and it is eliminated from the body in 2 or 3 days. So there's no concern about not being exposed to sunlight or to artificial light after the administration of radaporfin. Maybe 1 or 2 days, but not more than that. We were very encouraged. These are some old data, but just to show you the motivation of the work, we were very encouraged with use of radaporfin in treating a number of solid tumors in mice. This is an example of colon carcinoma. What we have here is what happens with the mice if we don't treat them, the control group. The tumor grows, and when it reaches a certain size, we have to sacrifice the animals. So initially we have 100% of the animals alive, but very rapidly, in less than 20 days, we have to sacrifice all the animals. When the treatment is done with radaporfin, we have 88% of the cures. Moreover, the animals that were cured, if they are inoculated again with the same tumor, the colon carcinoma tumor, they reject this tumor. This reflects the stimulation of the immune system by photodynamic therapy. And this stimulation of the immune system is also evident when you use nude mice, that is mice without an immune system, and these nude mice respond more poorly to the treatment. They can be treated, but not with this drug and light doses. In order to obtain cures, we need to increase substantially the drug and light dose. So there's an important component of immune response to the success of this photodynamic therapy with the photosensitizer that we developed called radaporfin. This encouraged us to go on to clinical trials. The clinical trial is now nearly completed. In fact, there's only 1 more patient that we have to treat to complete the clinical trial. The trial is in the treatment of advanced head and neck cancer. Typically, the patients have done all the possible treatments before. They are not responding to chemotherapy anymore. They are not responding to radiotherapy. They have gone through surgery. They cannot continue to do more surgery, and they are in palliative care. And it's patients that are in palliative care that were recruited for this trial. This is an example of a patient with a tumor in the neck in this region. This is a picture of the treatment. And what we have seen is that after 1 or 2 cycles of photodynamic therapy, and then later on the patient, the tumor disappeared, the patient became eligible for immunotherapy. This has been published in 2018. The patient is still alive without any signs of the tumor. So this is in fact a case of a cure of a patient that was in advanced, in palliative care. However, when we tried to do the same with the triple negative or the analogous triple negative breast cancer, which is the 41 mammary tumor in mice, we don't see basically any response, a very small response to photodynamic therapy with respect to control. There's a small difference, but very small difference with respect to control. But even worse than that, we don't see any difference from control with respect to the approved immunotherapies for other indications, not for indications, which is the immune checkpoint blockers, anti-CTLA-4, anti-PD-1 that are widely used now for other cancer indications. They do not have any meaningful effect on this 41 cancer or the corresponding triple negative breast cancer. The cancer is terrible because it very rapidly metastasizes to the lungs. This tumor expresses luciferases, so we can see the fluorescence or the chemiluminescence of luciferase from the lungs. This can be quantified, and what we are seeing here is that we have a very small effect on the primary tumor, and we also have a very small effect in the number of metastases in the lungs. So overall, none of these therapies is really satisfactory. We try to understand why this is happening, and this took us to photoacoustic tomography. Photoacoustic tomography is relatively recent, is still waiting for a good translation to clinical settings, but it's a very promising application of pulsed light. Because we are using radaporfin, and radaporfin has a peak at 750 nanometers, we can unmix the signal of radaporfin from the signals of oxyhemoglobin and desoxyhemoglobin. And when we do this unmixing, we can see we can see radaporfin in the tumors, in the tissues in general, after the administration. This very short video, it's a compression of images collected for 15 minutes after intravenous administration of radaporfin. What you see here is a subcutaneous colon carcinoma tumor. The red color is the increase of the signal assigned to radaporfin. So you see that in less than 15 minutes, you have lots of radaporfin in the tumor. And this is why the tumor is responding so quickly. However, if we do the same with the 41 tumor, now my student was very creative, and in this case, radaporfin is shown in green. Okay, radaporfin is in green. Although here in the colon carcinoma, you see lots of green inside the tumor. We can localize the tumor with ultrasound at the same time that we do the acoustic tomography. So you see lots of green here, and this is wonderful because the tumor is responding to therapy. Here you do see a little bit, of green, but very little. This can be quantified, and you see that there's a huge difference between radaporfin in the tumor in CT26 and 41 cells. We can see radaporfin because of its absorption spectrum. I'm also convinced that the reason why the antibodies are not working, and immune checkpoint blockers are not working in this case, is because they have very high difficulty in accessing the tumor cells. So there's a problem in administration. I will not now have the time to discuss how to improve this administration. We can discuss about that later when the talk is not being recorded. But here I am showing again, but now radaporfin is in yellow. My student actually was very creative with colors, so the radaporfin is in yellow. What you're seeing here is the same 41 tumors before and after the administration. Before we, in the previous slide, we had seen 72 hours. This is 15 minutes after the administration. There is very little yellow, very little radaporfin in the tumor. As mentioned before, this is difficulty specific to this tumor, and it was identified before. When we use some other methods to promote the delivery of radaporfin to the tumor, you see that the quantity of yellow increases appreciably even after only 15 minutes after the administration. Now we have more radaporfin in the tumor. We are going to do the photodynamic therapy. You see, this is a comparison from the previous data of radaporfin in the tumor with the enhanced administration or just the normal administration. And the fact that we have more radaporfin in the tumor makes the tumor respond significantly to photodynamic therapy. We now have an increase by a factor of almost 2 of the lifetime of the animals. This is also obvious from pictures. This is the result of the enhanced administration. 24 hours after the treatment, you see some necrosis. After a week, you see lots of necrosis, and the result is much more discrete if you don't do the enhanced administration. So just to conclude, so we have seen that we can use optical methods to make diagnosis of cancer. This is limited by poor light penetration in human tissues and sometimes poor contrast. We can increase the contrast, and Gleolan is a remarkable case of success for fluorescence-guided surgery. There are many products in pipelines of pharmaceutical industries to follow this path and use fluorophores attached to some kind of molecule that will preferably link to receptors expressed in the surface of tumor cells, or that will be activated and become fluorescence by some metabolic process. I believe we are going to see in the coming future many more products following this path. We also have seen that photoacoustic tomography solves some of the depth problems that we find in optical methods, but still lacks some cancer-specific contrast agents. I'm quite convinced that next talk will explore this further and show us some paths to follow. And I hope that you have also been convinced that if we add dyes, we are not just relying on endogenous dyes. If we add dyes to this process, we can increase contrast, and these dyes can also work as photosensitizers. And when they do, you have theranostics, because you can do the photodiagnostics and you can do, for example, photodynamic therapy essentially at the same time, and both detect and treat the tumors. This is a picture of my group taken last year, and I thank you very much for your attention.